Hello everyone, I am Fabien Coulon and I will present you our paper, Modular Distributed IDE. So let's start with a motivating example. This is the modeling environment of NabLab, a language for mathematicians and physicists to write numerical analysis algorithms. NabLab programs are mainly composed of jobs with complex data flow between them, and they are representing physical systems. As you can see, this modeling environment provides several views: a text editor to edit programs, a LaTeX view to display formula from the program with mathematical notation, a model explorer, an outline to get an overview of the program, and a graphical view to show the data flow between jobs. These views provide many language services. For example, the text editor provides a content assist, go-to references, a program validator, etc. There is also a compiler that takes NabLab program in input and analyzes a graph of jobs to generate efficient source code, since the simulation of physical systems may be expensive. All the language services of the modeling environment are embedded into the Eclipse IDE. So currently, if you want to have this development environment as a web application, you have this architecture: a client that remotely accesses the language services provided by a language server. The language server is a monolith that provides all the language services. What we want to do is to distribute all the language services across multiple execution platforms. The idea is now we have access to a diversity of execution platforms that vary in the resources they provide, like CPU or memory, and that at the same time we have heterogeneous language services with specific needs. So through the distributions of the language services, we want to best fit the needs of the services. To give some numbers behind this motivation, we measure the response times of all language services for the NabLab language with files of increasing size. We choose completion that propose content to be inserted into a program for a given offset. References, that is a go-to service. It gives ranges in the program referring to a given symbol. The rename service that replaces occurrences of a symbol by a new text. And compiler that performs graph analysis of the jobs from NabLab programs and generate Java source code. So we have a set of language services that are increasingly computationally intensive. So we measure the response time in this figure. Times are in milliseconds, and the scale is logarithmic. What we see is there is a clear hierarchy between the services. Completion is nearly constant, about 5 milliseconds. Then comes references that last less than 200 milliseconds. Then rename that starts to belong. It goes up to 7 seconds for the bigger files. And then compiler that lasts for about 15 minutes for the last file. So for the NabLab language, we have a diversity of language services, and we would like to be able to deploy them individually on different execution platforms. The distribution of the language services is not possible if they are provided by a monolithic server, so we cannot take advantage of the diversity of the execution platforms. We have identified two challenges for the distribution of language services. First, how to modularize the language services to benefit from the resources of multiple execution platforms. We need language services as deployable units. And because a language can have many services, how to automate the modularization of language services. The second challenge is the configuration of the deployment of language services. How can we safely configure the deployment of the services to ensure that the resulting distributed IDE works? We want also to be dynamic, because the needs of language services are related to the current activity of the language user, which can change over the time. Our approach for the modularization or the distribution of an IDE consists in two steps. First, the IDE microservization, and second, the IDE deployment. The idea is to start from an IDE specification composed of a language specification and a protocol specification. The language specification is classical, an abstract syntax, concrete syntax, and semantics. The protocol specification describes a set of language services and their relationships. From this specification, we generate microservices on the feature model. The microservices implement the language services, and the feature model describes the variability in the possible deployment of the language services. For example, which services are mandatory and which services are alternative. Then, in the second step, we use this feature model to drive the deployment configuration, which consists of a language user who selects the language services to be deployed and defines where to deploy them. The feature model ensures that the configuration is valid according to its constraints. At the end, the microservices are distributed across the different execution platforms as defined by the configuration, and the client can call the language services remotely. To specify communication protocol, we have implemented a domain-specific language with this text. At the right, you can see an excerpt of the specification for NabLab. Our DSL allows to define the language services, here storage and completion. Each one of these can have multiple capabilities, which correspond to collab functionalities. For storage, we have, for example, document that is used to retrieve the text of a program, and update that is used to change its content. And completion has the capability complete that returns the list of proposals. We also allow to specify the dependencies between the services. Here we said that complete is calling document, and we can also specify that a service is mandatory in the deployment. That is the case for storage. For the microservices, we rely on Quarkus to implement them. It is a framework based on annotation of Java classes and Java methods to define the entry points of microservices. The generated feature model is based on a feature ID. That is an Eclipse plugin dedicated to the formalism of feature models, which provide editors to customize the tree of feature by a language designer. And for the deployment part, microservices are containerized with Docker, and we use Kubernetes to orchestrate their deployment. To evaluate our work, we apply our approach on 4 Xtext-based languages: NabLab, Logo, that is a programming language for 2D drawings; SwingML, that is a language dedicated to application for the Internet of Things; and MiniJava, that is a subset of Java. For these languages, we compare two architectures, a monolithic server and microservices, and we measure the response times of language services on files of increasing size. The first thing we wanted to know is can we improve the response times of language services by distributing them. We had a monolithic server on a laptop and we accessed it locally. This is figure 1 at the left that I presented earlier. And now we deploy its language services as stateless microservices on a cluster with powerful machines. But we access the language services remotely. This is figure 2 at the right. So better machines, but with modularized services and with network communication. In figure 2, we have indicated in the percentage comparison with figure 1 for each response time. The first things we see in figure 2 is that the hierarchy between language services is the same as in figure 1. Completion on references implemented by microservices have bad response times. Now completion is no longer constant. Its response time increases with the file size, and references last longer, almost double its response times. But rename and compiler are better as microservices. Rename has gained between 16 and 25%, and compiler between 9 and 21%. So we show that there is a benefit in distributing the most computationally intensive language services, but for other services it is better to deploy them locally. To understand the differences between monolithic and distributed architecture, we show in this figure the response times of the language services of the monolithic server in blue and of the microservices in orange. All the server and microservices are deployed on a cluster and are accessed remotely. For the microservices, we highlight in gray the parts of the times due to the modularization of the language services and the communication between the microservices. This figure shows two things. Language services implemented as stateless microservices perform poorly compared to their implementation in monolithic servers. And the overheads of the microservices are not due to the modularization or the communication between microservices. Since we have implemented language services as stateless microservices, and that monolithic servers are stateful, we investigated the statelessness impact. We use Xtext and EMF to load a model from the textual representation of a program before computing the internal logic of the language services. EMF loads model lazily. There is an initial cost to build the content tree. That is what we have measured in figure 4 for the 4 language in dark blue. And then model references are resolved on demand. The light blue part in figure 4 correspond to the resolution of all model references. This means that the impact of the model loading depends on how much a language service traverses a model. To compare these model loading times, we show in figure 5 the response time for completion, the first row of plots, that is a service running through a few references, and a document symbol that's running through many references in the models. The orange curve represents the time for the stateless microservice, and in blue the time for the stateful monolithic server. This figure shows that the difference between the two architectures is at least equal to the initial loading time of the models, and that a service browsing the whole model can have time close to the time necessary to resolve all the references of a model. To summarize this talk, for the distribution of language services, there is a benefit for a computationally intensive service, but others should remain local. The modularization of the communication between microservices add only a small overhead to the response time of the language services. And implementing language services as stateless microservices can be costly, and it is due to model loading. We identified 3 important research logs. Firstly, we experimented stateless microservices, and the load of model is costly. So there is a need to investigate how to access the model. determining the best location for a model, and proposing caching or replication techniques are leads to explore. Another point to explore is deployment directly inside the web browser to minimize latency. WebAssembly may be an interesting target for our microservices generator. And the last point we want to explore is the self-adaptive deployment of the language services. The idea being that the deployment of the services is fully automated and reacts to changes in the variable execution platforms, in the need of the services, or in the user activities, so that we always have the best deployment. So this is the end of my talk. Thank you for your attention.